wall it hits, right? When it hits, everything about the velocity. So we want the velocity in vector component notation. We want an angle magnitude. We also want to know this height here. Yeah? Now the good news is that we've done a lot of the work already. We just need to do a few more kinematic formulas. Okay? The good news is, and this is just a different sort of one.
Wait, so we're doing the whole problem again with
Yeah.
all over again?
No, almost though. You'll see there's a shortcut we can take to save some time. So shortcut number 1 is that everybody knows that's 0, that's negative 9.8. Shortcut number 2, isn't it the same launch? So aren't the initial velocities exactly the same? Yeah, that took us like 20 minutes to figure out, right? So 27.099, 12.636. Right? Well, okay, but that was when it would hit the ground again. So we better hold off on that one, right? It's not hitting the ground, so that's not true. Right, so that's why I wanted to give you one example where it's not true. Okay? But this is true. And then where does the 50 meters go? X horizontal, yeah, exactly. Right? Now, let's do some predictions here. When it was allowed to hit the ground, it went 69.9 meters. So it's going to be way over halfway. Yes? So doesn't that mean that it's going to hit this wall lower than, what did we figure out, 8.14 meters? That was the greatest height. It's going to be on its way down, so it's going to be lower than 8.14. I predict also that the final velocity is in the vertical direction is going to be a negative number, because if you look at this, it's gone up and it's coming down again, yes? So I predict a negative number, but let's just see what shakes out, right? Okay, now, this is all we know. Is this side solvable yet? No, we need 3 things. We only know 2. But is it likely that we can find the time? Yeah, we can find the time to solve this. I always have time. Right? So, how do I find the time? What's the formula on this side? Remember, it's just really simple. On this side, you're going to use this. It's always this. X is VIT. It's really plus 1f at squared. But since the acceleration is 0, that goes away, right? Okay. So if 50 equals 27.099 times t, solve for t. Solve that for t. Right. You nilly. 1.845. There he is. Do you guys get 1.845? I got 1.845.
Wait, I wasn't doing it. What did we say?
What were you doing? Do it. Are you? That's what you're doing. All right, I've got it. Yeah, he's like varsity physics. Yeah. I wonder if the wireless microphone works. You got a Finnish one, right?
Yes. And I'm really scared because I don't exactly know what's going on, so I'm probably not going to improve that much.
There you are. Here you go. Okay, there's that, and then here's a data packet. But this is going to be a high-class YouTube video. I'm on camera, I'm off camera. The only thing I could do to improve it would be like to go to the bathroom or something in the middle. Okay, did everybody get 1.845? What do we do with the 1.845?
Put it over there on
Yeah, we slide that guy across, right? 1 point. Okay, and then, G, how are we going to solve for the final velocity and the displacement? Yeah, this one will work right here, right? So use VF is VI plus AT. And then this one is your choice. Okay, do that right now. You solve, rather than watching me solve, you guys solve for what this final velocity is and what that x is using this time, because that time's correct. Did you guys get negative 5.446 for the final? And then for x, I use, just to mix things up, I use 1/2 VI plus VF times t. Do we get that? So now we know everything. We are like the uber mensch when it comes to this problem, right? We know that at 50 meters horizontally, it's 6.63 meters in the air, which is less than 8.14 like we predicted. If it was bigger, why we would be a little bit suspicious, right? We know that at that instant that it started off from the ground going over 27.099 and up 12.636, but now it's still going 27.099 over, but now it's on its way down. So if we drew a picture of it, and this will be the last thing we do, right? If we drew a picture of this guy, it would look like this. 27.099 over 5.446 down, right? That angle is that's 11.4 degrees. And then the hypotenuse here, the magnitude, is the square root of 27.099. So, class. So, on this problem, this is what we know, okay? We know that when it hits, it's going this meters per second in the x direction, right? Plus this meters per second. Can you be quiet, please? All of you? Hello? Okay. So it's going this meters per second in the x direction. It's going this meters per second in the y. That's vector component notation. We know angle magnitude, that it's 11.4 degrees below the horizontal when it hits this thing, right? Okay. It's the magnitude, the speed that it hits the building with, or whatever, is 27.6, which is really close to the actual launch velocity. It'll reach that speed, of course, when it hits the ground. Okay. There we go. You guys are the masters